try to genuinely keep up with everything today, it feels overwhelming, right? Just so much information flying around. How do you actually get a handle on important, complex areas? That's really what we aim for in these deep dives. To give you a kind of shortcut, pulling out the core ideas from the materials you send us. And for this one, we're looking at STEM, science, technology, engineering, mathematics. But not just as separate subjects lined up. We've got some great sources here, an article and a video from an expert that offer a really interesting way to see how they all connect. It's about finding those, let's say, independent variables for thinking about STEM. So we're going to unpack the systems view of STEM, then look closely at measurement systems, and finally explore some really different environments where STEM happens, all based on these sources. Ready to jump in? Okay, so let's unpack this core idea. The main thing from the sources is viewing STEM not as, four isolated towers, but as an integrated system. Why is that view valuable? Well, the material suggests it helps basically everyone from students just starting out to experienced colleagues see the connections, how it all works together.
Yeah, and what's really helpful is this analogy they use, the system box. It sounds simple, but it's powerful. Basically, you imagine a box. Inside, there's a process. It takes input, does something, and produces output. And crucially, the whole box sits within an environment. It's a framework for thinking.
Right. So thinking inside the box is focusing on that process, like what's happening in your lab or your house maybe. But the outside the box part, the environment, is just as vital. What's happening outside, the weather, the market, whatever affects what goes in and comes out.
Exactly. The environment shapes the inputs and influences the outputs. The source is really clear. You can't just think inside the box. You need both perspectives.
And those inputs and outputs, the source breaks them down into three main types: energy, material, and information. Pretty much everything flowing in or out fits into one of those.
Okay, so we put STEM itself into this system box. Where do the pieces fit? The sources position science as the primary input. It's where we get the basic knowledge, the discoveries, the parts to build with, learning new stuff.
Okay, science is input. Then the process. The part inside the box where the work happens. That's mathematics and engineering. Math helps you figure out what you're going to build, the design, the calculations. And engineering is the actual doing, the building, turning those inputs into outputs.
Right, which leaves technology as the main output. It's the result of the process. The tools, the inventions, the software, the tangible things that come out of applying science, math, and engineering. It's the tool-making process, as the source puts it.
And here's where it gets really cool, I think. The sources talk about a feedback loop. The technology that comes out, it doesn't just stop there. It cycles back.
Exactly. Those new tools, new instruments, they become inputs for science. They let us do better science, maybe even new kinds of science, which leads to new discoveries, new inputs, which fuels more engineering and math, leading to even newer technology. It's a cycle that accelerates itself.
That's such a key insight. It explains why progress feels like it builds on itself. And it changes how you think about a STEM professional, doesn't it? According to this view, they're not necessarily just super specialized in one letter, S or T or E or M.
Right. The source suggests they're more like jacks of all trades, but masters of understanding the whole system. They get how the science input flows through the math engineering process to create technology, and importantly, how that technology feeds back. They understand the connections, the entire flow.
Okay, that's the big picture of STEM as a system. But a huge part of STEM across the board is measurement, right? Measuring things accurately. It makes sense to think of measurement itself as another system, nested within that larger STEM system. The sources explore this too.
Absolutely. Think of a measurement system as its own box. Same principles apply: input, process, output, environment.
Yeah.
The core purpose is to take some data, a property you want to know, like the temperature of your coffee, and turn it into useful knowledge.
So how do you get that data, that temperature, out of the coffee and into your measurement system? You need a transducer. The sources explain this as basically a sensor, a device that converts that physical property into information, usually like an electrical signal or some other response we can work with.
Exactly. A thermometer is a classic example. From the material, it transduces heat energy into the physical movement of liquid. That's the information. Or a microphone turning sound waves into electrical signals. Force sensors, like in that old Wii balance board, turning pressure into signals.
Your phone's accelerometer, knowing if it's upright or sideways.
Yeah. Or even a simple touch sensor on a fridge door. They're all translating something physical into information.
And getting that translation to happen often takes energy, right?
Okay.
To push the data through the transducer.
Yes. The sources highlight different energy types used in measurement. There's kinetic energy, like in mass spectrometry where you fling molecules to measure mass. Potential energy, think gravity for scales using force sensors, or electrical potential in chemistry measurements. Heat energy for thermal analysis, and light energy, which is fundamental for spectroscopy, shining light on stuff.
Okay, so we have data, a transducer using energy, giving us information, but like you said with the thermometer, the line going up isn't the final answer. How hot is it?
Right. That raw information needs interpretation. That's where the model comes in. The model is another tool, often software or an algorithm, that takes the raw information signal and converts it into actual knowledge, something meaningful. The numbered scale and the thermometer glass. That's a simple model. Complex weather forecasting uses vastly more complex models. It's the bridge from the signal to understanding. It's how the information interfaces with us.
The sources also touch on helper processes, like needing to separate things first. Chromatography comes up.
Yeah, that anecdote about separating leaf pigments to understand fall colors. Sometimes you have to isolate the thing you want to measure before you can even point a transducer at it. It's a pre-processing step.
So if you, the listener, wanted to actually build one of these measurement systems, what do you need?
Well, the sources point to key ingredients. You need electronics, the hardware, the circuits, maybe interfaces like an Arduino or Raspberry Pi. You often need a physical box and enclosure. And the source notes how 3D printing is becoming common for making these custom housings.
And definitely software. You need code for the model, for processing the information, maybe controlling the hardware. C++, Python are mentioned, and LabVIEW gets a specific shout out.
Yeah, that LabVIEW example at SpaceX is powerful, using it to create virtual instruments on computers for testing rocket components. It shows how hardware, software, and these measurement principles all come together in really critical real-world applications.
Speaking of the real world, let's talk about the different environments where these STEM systems operate. It's not just a quiet lab bench.
Not at all. The sources give some great examples. A wind tunnel, for instance, using things like pressure-sensitive paint on model aircraft viewed by digital cameras to map airflow. That's a measurement system working in a specific aerodynamic testing environment. It's been around since the 90s, apparently.
Then there's biomedical research, studying cells, maybe using huge, complex machines alongside microscopes, all feeding data onto screens. That's another distinct environment.
Manufacturing plants, too. Think of an auto assembly line. It's packed with sensors, robots, measurement systems, ensuring everything fits, everything works. Quality control is all about measurement in that environment.
And things get really challenging underwater. The manta ray autonomous vehicle is mentioned.
Right. A platform needing sensors for everything from temperature to maybe detecting tsunamis. Designing systems to work reliably down there is tough. The source even hints this is vital for potential future ocean colonization.
And the ultimate remote environment discussed, Mars.
Yeah, the Perseverance rover, described basically as a mobile laboratory, a platform loaded with measurement devices, cameras, spectrometers analyzing rocks, weather stations, even radar looking underground, all sending knowledge back, helping us understand the planet, maybe paving the way for humans later.
So wrapping this up, what's the big takeaway here? Looking at the sources, it seems seeing STEM as this interconnected system, understanding the flow from science input through math and engineering to technology output with that crucial feedback loop, and recognizing measurement itself as a key system within that, it gives you a much more integrated picture, doesn't it? More than just four letters.
It really does. And it reframes what being a STEM professional means. It's not just about depth in one area, but understanding how all the parts collaborate to solve problems, to create knowledge wherever that needs to happen, in any environment.
Yeah, the adaptability of this systems thinking is pretty amazing when you think about it. You can apply this kind of box framework, input, process, output, environment to understand so many different things, your body, a business, space exploration.
Which leads to a final thought for you, the listener, to mull over. We've seen how vital measurement systems are in extreme places like deep oceans or Mars, places we're just starting to really explore, considering environments that might be even more alien or challenging in the future. Maybe asteroids, other star systems. Who knows what completely new kinds of measurement principles or system designs might we need to invent? What does the next generation of transducers or models look like for places we can barely imagine today?